3.
Hello everyone, the title of our senior project is Hydrocyclone Water and Oil Separator. My name is Patrick Baghomian.
I'm Saul Pedroza.
I'm Jonathan Fernandez.
And I'm John Linardi. Our advisor for this project is Dr. Henry Shui.
Hydrocyclones are devices used for separation of solid and liquid, gas and liquid mixtures. This project concentrates on liquid and liquid separating hydrocyclones. They are mostly used in the oil industry for separating water and oil. The picture on the top right shows what they look like. Many hydrocyclones next to each other held together inside a cylindrical vessel. Before hydrocyclones, only gravity tanks were used for separation. Gravity tanks have a higher capital and expense cost, are bulky, and have many components compared to a hydrocyclone. Also, gravity tanks alone started not to meet stricter government regulations for the oil content in the wastewater being pumped back into the environment. Maximizing the efficiency of hydrocyclones is important because it will lessen the pollution of water and increase profits by recovering more oil. Martin Dew and Derry Coleman from University of Southampton were the first ones to perform experiments and recommend a liquid and liquid hydrocyclone design for best efficiency. The recommended design is shown on the top right picture with ratios of hydrocyclone geometry. DC is the cylindrical diameter, DI is the inlet diameter where the mixture enters the hydrocyclone, DO and DU being overflow and underflow diameters respectively. L cylinder is the length of the cylindrical portion, alpha and beta being the two conical section angles, and LU the underflow length which starts after the second conical section ends. Grant Young later performed its own experiments using Coleman and Dew recommended design and managed to obtain higher efficiencies at flow rates by making some modifications. Young's recommended modifications can be seen in the lower picture. He eliminated the first conical section so that the hydrocyclone will have one cylindrical and only one conical section, increased the beta angle, and also made changes as seen in the picture to some of the ratios. The purpose of this project is to build a recommended Young design hydrocyclone and test it by performing experiments for its efficiency. Then build a second hydrocyclone with our own modifications to the Young design and to see if better efficiencies can be obtained. Oil and water mixture enters the hydrocyclone through the tangential inlet connected to the motion of the mixture is created and the mixture flows to the underflow. The rotational motion creates a centrifugal force acting on the mixture. Due to the difference in the density of water and oil, the heavier liquid, in this case water, is forced to the outer boundary of the rotational motion near the hydrocyclone wall. The lighter liquid, which is the oil, rotates in the center along the center axis of the hydrocyclone. The mixture must have a tangential velocity high enough such that it creates a centrifugal force strong enough for separation to take place. Lowering the inlet diameter is one way to increase the tangential velocity of the mixture, but this also increases the probability of the oil droplet sizes becoming smaller because of high flow resistance. As a result, this will make separation more difficult to achieve. Analyzing the oil droplet size is beyond the scope of this project, but it should be mentioned. Having a greater density difference between oil and water also aids in separation process. For oil to exit the overflow, a back pressure must be applied. This back pressure creates a vortex in the center of the hydrocyclone, causing the oil to exit the overflow. Without this back pressure, the entire mixture will exit the underflow. The amount of back pressure should be determined on the field based on trials and experimental data and is different for every hydrocyclone. And finally, since the concentration of oil inside the mixture is known in our experiments, the efficiency will be calculated by comparing the concentration of oil in the underflow with the concentration of oil in the mixture.
Before we begin our calculations, I'll first go over our experimental process. Looking at our system diagram, the oil-water mixture will be held in a tank labeled 0.1. At this point, the ball valve on the underflow would be open while the ball valve on the overflow would be closed. Then using our pump, the fluid would be transported to the inlet of the hydrocyclone. Since there is only one exit, the entire oil-water mixture will go through the underflow. Once there is a steady, continuous flow through the system, we will begin to simultaneously close a ball valve in the underflow and open the ball valve on the overflow. We started our calculations by first establishing some initial conditions. For our oil-water mixture, the oil that we chose to go with was SAE10 oil at a 10% concentration. From the different oil that is available to us, SAE10 gave us the greatest density difference from the water, increasing our ability to separate oil from it. To increase the visibility of the oil in the water, we plan to add dye to it. We also had to estimate our length of the pipe used and the number of fittings, as well as the height of the level of each tank. We also made multiple iterations of our calculations using different pipe diameters, and we went with one that gave us the best desired results based off of our research. The ideal flow rate that generates the higher efficiencies in oil separation is between 20 and 30 GPM. For the sake of our project, we went with 25 GPM. Also, having all three tanks exposed to the atmosphere not only helps us by simplifying our system energy equation, but it also eliminates the possibility of having completely pressurized vessels in our system. Given our parameters, we needed to find the proper pump required for our system. Bernoulli's equation helped us mathematically model our project, which helped us with the pump selection. Next slide. Given that the majority of the information about the hydrocyclones comes from experimental data, finding a way to calculate the head loss that the hydrocyclone itself would provide to our system required extensive research. We had to make sure that our setup and fluid mixture was used in a similar fashion as ours. Thanks to Asoma and Nauyer's-Munn's hydrocyclone model, we were able to do so. Finally, we were able to calculate the amount of head required to be supplied by our pump, which is found to be 26.463 feet. And if we convert this to horsepower, it gives us 0.6165. Selecting a pump that would supply our necessary requirements and also be able to be used in low oil applications was another challenge. Because there's a great price difference between pumps used solely for water or oil, we had to interact with multiple vendors to see if we could use their products. For each product we considered, we derived performance curves for the ones provided by the manufacturers. Using our pump similarity rules, we created graphs to help us analyze the pumps. The two graphs at the bottom are from the pump that we selected, which can be seen in the top right picture. The dark blue line is our system curve, which we got using Bernoulli's equation. And the other colored lines are the pump curves at different speeds. We had to make sure that we stayed to the right of our system curves where they would intersect the different curves from different speeds, because this would assure that our system was stable. The graph on the right shows a magnified region of what was important to us. From it, we conclude that we must run our pump at a speed of about 2,050 RPM.
Moving on to the initial design or our baseline. Our initial design is made by using the Thiel-Coleman's parameters. We are also trying to enable the use of Schedule 40 piping, where 3/4 inch piping is used for the inlet and 1/2 inch piping is used for both the overflow and underflow piping. We are opting for a 1/4 inch wall thickness to accommodate for pressure buildup that will be on the hydrocyclone during operation. We also added fillets in the connection between parts to try to avoid any stress concentrations in the connections. For our second design, we are going with the removal of the cylindrical portion near the inlet based on Young's recommendation. For this design, we're still using the same inlet, overflow, and underflow diameters in order to fit into the test tank. It is also important to keep the distance between the inlet pipe and the center of the hydrocyclone, and the distance and between the overflow and underflow to be the same while modifying the design so it could fit into the test tank. And also by the same reason, we also have to angle the inlet by 3 degrees in order to accommodate any changes in this design.
Going into this project, we knew that fabricating our hydrocyclone was going to propose a challenge. Machining it out of metal would have required us to have a great deal of prior knowledge to working various machines, and more importantly, experience. If not, we would have to rely heavily on outsourcing the prototyping process, which would require an extensive amount of lead time and money. Thankfully, here at Cal Poly, we have a great resource when it comes to helping young engineers bring their designs to life. Thanks to David LaFay, one of Cal Poly's mechanical engineering department technicians, he showed us the technology the university has readily available to us. Using the Formlabs 3D printer, which uses resin as a filament and high power density laser over the 3D printers that use spools made out of various materials, we were capable of meeting the requirements of our hydrocyclone. This printer allowed our prototype to have a superior printing resolution and smooth surface finish. This printer also gave us the best clarity when using translucent materials, which was important to us since we want to be able to observe the separation in real time and encapsulate the theory behind our project. The curing process not only made our prototype harder, but it gave us imperishable characteristics needed for our application. As previously stated by Patrick, the hydrocyclone's dimensions were governed by Young's recommended design criteria, which resulted in producing the highest efficiency from all the experiments we studied. Based on Young's design criteria, our original hydrocyclone dimensions were beyond the 3D printer's printing range and results into redesigning the original one-piece design into a 3-piece assembly. For the sake of this project, to maintain continuous flow throughout the system, a custom holding tank was designed. To keep the overall cost of the project low, we designed and fabricated this tank ourselves. The overall dimensions of the tank are 12 inches by 18 inches by 24 inches. The tank was constructed out of 3/8 of an inch clear acrylic sheets. These sheets are specifically chosen because of the material strength, transparency, cuttability, and availability. Metal brackets, bolts, and nuts were used to hold the tank together. Furthermore, to prevent any leakage, thread sealant was used in each bolt, and an acrylic sealant was used in all of the inner edges of the whole tank assembly. The tank consists of 2 different levels and 3 holding chambers. The top level of the tank divides into 2 holding tanks. One of the tanks is where the underflow is collected, and the other tank is where the overflow from the hydrocyclone is collected. These tanks have individual valves that allow the tank to drain back into the bottom layer, which serves as our original mixture's holding tank. Each tank has a perforated lid that can easily be removed for easy sample collection. Moving on to the driving component of this project, the pump. Sizing and choosing the correct pump to power our system was driven by our calculations and our mixture's concentration. As covered earlier by John, our system only required a pump with 0.165 horsepower. The pump was going to be the most expensive component of our system. The pump we selected was a 115 per 230 volts 3-phase centrifugal pump. This pump was capable of providing half a horsepower, which is more than enough for our system. Because the hydrocyclone must have a flow rate of 25 gallons per minute, the pump must be controlled by a variable frequency drive. The variable frequency drive would help us control the RPM that our pump would provide given our system's demand. This also gives the ability to test multiple different speeds and adjust accordingly to try and increase the separation efficiency of our hydrocyclone. Lastly, for all the piping of our system, we decided to utilize 3/4 of an inch clear PVC Schedule 40 piping. Installing clear piping in our system allows instant visualization as to how effective the system runs and allows us to make necessary modifications to the flow or back pressure generated in order to increase the efficiency. This particular size and material of piping was chosen because of its availability, low cost, strength, and it being a standard size, which would make the entire assembly process of our system much easier since connections, keys, and other components may be found to be a direct fit. Here's the complete model of our hydrocyclone setup.
All right, so to conclude, although our design build phase is complete for our baseline design, due to unforeseen circumstances, we were not able to test it. The closure of the engineering labs meant that we were no longer had a safe place to test our project. Also, the testing equipment needed to measure the concentration became unavailable as a result. In the future, baseline performance will be tested first and a flow pattern will be observed so that we could see if we could get a vortex to form inside our hydrocyclone. On the initial test, we would also see how efficiency would change by varying the flow rate. We would also have to observe how changing the back pressure by manually adjusting the ball valve on the underflow affects the separation. And then once initial testing is done, an implementation of an internal ribbing on the hydrocyclone near the inlet would be considered, depending on the initial flow patterns that we observed. Initial internal ribbing theoretically should guide the fluid to enter the helical motion earlier, hence increasing separation for the same length of our hydrocyclone. Ultimately, we are left with an unfortunate feeling of not being able to see our project come to completion. However, with our documentation and recommendations, a future group should be able to build upon our work and be able to determine if we can increase the efficiency of Young's model so that it could potentially be applied to the oil industry. Thank you.